Okay, hi everyone, I'm Gabriel, and today I'm presenting FlexLLM, a project that allows us to make GPU clusters dramatically more efficient by multiplexing LLM inference and fine-tuning on the same GPUs. And all of this without breaking the inference latency SLOs. So to begin, we need to first introduce what is fine-tuning as a service. So that's a new trend, a new type of AI service that's becoming popular these days. And it allows users to fine-tune a provider's AI models. These AI models can be closed source or open source. And all of that while using the provider's resources. So one of the most famous such service today is probably Tinker from Thinking Machines. But it's really not the only example. Most major AI companies at this point offer similar APIs. So under the hood, fine-tuning as a service, such as Tinker, tend to use like parameter-efficient fine-tuning techniques, such as LoRa, in order to do this efficiently, to allow many users to essentially share the same backbone model and only train small adapter parameters. So this is exactly the type of workload that FlexLLM is designed to power efficiently. So how do these providers deploy fine-tuning as a service on their infrastructure today? Most of these providers offer both fine-tuning and inference services. So they have their cluster, and they have to decide how to divide the resources between the two workloads. So for the vast majority of providers today, the answer is resource isolation. So you just you divide like the classes that you have, and you have two completely separate clusters, one for inference and one for fine-tuning. So one cluster will serve latency-critical inference requests, and the other one will process more compute-intensive, throughput-oriented training jobs. And this strict separation has many advantages. There's no interference. Scheduling is much more flexible, and so forth. So it makes sense to do it. But unfortunately, it also comes at a very big cost. And so the big problem is that so if you use separate clusters for inference and fine-tuning, we will most of the time face GPU underutilization. So here, this diagram shows like the typical utilization for the two clusters. So for fine-tuning, we can get pretty good utilization. But for inference, often we have wasted capacity. We have this value of wasted capacity. And the reason is SLOs. So because we cannot predict when inference requests will come, and there's very strict requirement for response times, we have to over-provision GPUs. And then when a burst comes, we will use the excess resources to process this request very quickly. But then like when there's no burst, most of the time, then you have underutilized GPUs. And the strict separation between the two clusters make it so that it's very, very difficult to move some fine-tuning work into the inference GPUs. Because if you do that, then it will take too long to stop that work when the next burst will come, and we might break otherwise the SLO. But if we think about it, these two workloads are otherwise, besides this problem of how to schedule them together, they're really complementary, because inference is latency sensitive, but it is bursty and predictable. On the other hand, fine-tuning is more throughput sensitive, so it's a bit more predictable, but it's a bit also more tolerant of delays. The jobs are much longer, so a few milliseconds of delay here and there is not a big problem. So if we could really find a way to multiplex these workloads together on shared resources, we would really be able to increase utilization by a lot. So we actually found a way to do it, and we call this approach co-serving. So the principle is pretty simple. So when inference demand is low, fine-tuning expands to use the spare capacity. And then when an inference burst comes, the fine-tuning shrinks really quickly to yield the resources back to inference. And in this way, the combined utilization stays high throughout and is very reactive to avoid delays when more inference requests come. So we'll see how to do this in practice. That's the challenge. So let me explain how this works mechanically. So on the left, we see an illustration of the LoR architecture, which is the most popular parameter-efficient fine-tuning techniques, or one of the most popular in use today. So for each target module, for example, here the target module will be the blue big circle, big square of pretrained weights. We keep the backbone, the big module, frozen. So we don't change that if we want to fine-tune this parameter for many users. Instead, we add a bypass. We add two low-rank matrices, in this case here A and B, which are much smaller. So they're very cheap to fine-tune. And we can fine-tune a lot of them in parallel. And then what we do in FlexLLM is we actually fuse in a single kernel the forward pass for inference and for fine-tuning. So fine-tuning has a forward and backward pass. So the forward pass can be fused with inference in a single kernel. And this is what we can do at the first step. And then at the second step, we can run a next step for inference. And then on a separate stream, we will run the fine-tuning backward pass. So in this way, we can run the two things, multiplex them using the same GPUs. And the good thing is that the pretrained weights, the backbones, can be allocated only one time. So if you have two clusters, you will need to duplicate the weights on the two clusters. But in this case, since you're using the same resources, the same backbone weights can be shared. Now, a lot of problems that we'll have to face if we do this. And the first one is memory. So if you ever tried fine-tuning some model, you notice that the amount of memory that you need to do fine-tuning is much larger than the memory that you need to do inference on the same model. And that's because you need to, first of all, allocate gradients, tensors, for all the weights that you're training, and also like intermediate activations, and so forth. So we need to figure out a way, if we want to run these works on the same GPUs, to reduce the memory utilization. And to do this, we use static compilation. We use a graph pruning technique that will go through the computational graph at the beginning, analyze it, figure out which tensors are really necessary for the backward pass and which ones are unnecessary. For example, the gradients for the weights that are frozen, those are mathematically unnecessary. So we can prune them, as well as other tensors that might not be needed, or tensors that are for example, activations that are needed, but we find that it's cheaper to recompute them than to save them. So our compiler will automatically analyze this and do the pruning automatically, which results in up to 80% memory saving. So thanks to graph pruning, we solved the memory problem. And next, parallelization. So imagine if you're serving or fine-tuning a very large model, it will not fit on a single GPU, so we have a big cluster with many GPUs. We have to parallelize the model. And then we also need to parallelize the adapter model, the LoRa or other PFT. And there's many maybe PFT running in parallel. So really, there's so many different ways that you can do parallelism. So in this slide, we can see like for just very simple adapters, so each tensor has multiple dimensions, and each dimension can be parallelized differently. You can split it across different shards, you can replicate it, or you can not parallelize it at all. And so this compounds in a combinatorial explosion, very difficult to do it manually, and if you want to really get the optimal setup. And you also need to make sure that the parallelization is compatible. So like operators that use the same tensor will need to materialize the tensors on the same device. So we want to take this problem away from the users, and we use another compiler technique to at the runtime analyze the graph, and thanks to some profiling information, some lightweight profiling information, we can optimize the parallelization for both for the model first, and then for all the PFT that are attached to it. And next, the problem is how to make sure that fine-tuning task, if you're running in parallel, essentially fine-tuning task, fine-tuning forward pass, and the inference forward pass, and then fine-tuning backward pass with the inference forward pass, how to make sure that we don't break the SLO. So fine-tuning tasks are usually much more time-consuming. So if you're using the separate cluster approach, the default today, I'll show the timeline of how that works. It's much simpler to do it. So on one GPU, you're running all your inference tasks. So for example, you have different steps of inference. And you can see that there's no stall in between them, because as soon as you finish one inference step, one inference forward pass, you immediately have all that you need to start the next step. You don't need to wait on anybody. And fine-tuning is similar, and we can run on a separate GPU completely independently. And you have a forward pass, backward pass, forward pass, backward pass, and so forth, which are much longer. And there's, again, no stall, and the two workloads don't really interfere with one another. So if we instead try to multiplex the two things together, the naive way to do it would be to, so yeah, you can fuse in a single kernel the forward pass for inference and fine-tuning. And you have like a kernel, and then you have a first stall, because the fine-tuning forward pass will take longer. So you have to wait for that to finish before you start the next inference step. But there will be an even bigger stall afterwards, because after the second inference forward pass, if you're synchronizing after each step, we have to wait for the backward pass, which is extremely time consuming, and so forth. So if we repeat this for each step, in the same amount of time, we can see that we have run much less inference steps. And so we will definitely break the SLO. We cannot really do it this naively. So here's how FlexLLM does it instead. So to be able to fuse the work, we still fuse together in a single kernel, the forward pass for inference and fine-tuning. But we spread, we do what we call incremental fine-tuning. So we spread the fine-tuning work across different steps. So for the forward pass, first of all, we do token level fine-tuning. So that consists of distributing the tokens from the batch across multiple steps, across different forward passes. So in this case here, it will take us 1.5 steps, for example, to finish the forward pass. And then, similarly, we distribute the backward across different steps. So for that we do layer level fine-tuning. So instead of doing like a full backward pass for all the layers of, say, the model, the LLM, we'll only do, say, at first the last 2 layers, and then the second last 2 layers, and so forth. And so this allows us to, as you can see here, remove all the stalls. Because basically we make sure that the fine-tuning work takes exactly the same amount as inference step. So no delay is added, and we are able to meet the SLO. OK, so these are the key techniques, and let's see how we did in our end-to-end evaluation. So we ran some experiments using some standard models of different sizes, from 8 billion to 32 billion. Tensor parallelism degree, and standard inference workload, ShareGPT, as well as some production traces from Azure, ShareGPT to other arrival times. And for fine-tuning, we use a reasoning model fine-tuning dataset. So as baseline for the separate approach, we use VLLM for inference and Llama Factory for fine-tuning, so two like famous and high-performance frameworks. So here's the result. So in these slides, we have 3 panels. So for a particular model, in this case, 32 billion, we check 3 things. So first of all, we measure the SLO attainment. So any serving strategy that will break the SLO is not acceptable. So whatever we do, we first need to make sure that we meet that. And then given that the requirement is met, we will want to, of course, optimize inference and fine-tuning throughput, ideally both. So here, first of all, we compare FlexLLM with the separate clusters baseline. So assume we have the same amount of resources. We can decide whether to run inference and fine-tuning separately or run them jointly using all the resources together. So if we take the separate approach, there's different ways to do it. We can split the resources in different splits. So we can, for example, use 1/4 resources for inference and 3/4 for fine-tuning. This would be the orange curve. Or split them half and half, or the other way around. So let's take a look first at the SLO attainment. So as the arrival rate is low, all the curves look good. But when the arrival rate spikes up, then only 2 curves are acceptable, the blue and red curve. So that's FlexLLM. And the red curve corresponds to using 3/4 of resources for inference and 1/4 for fine-tuning. So given these are the only 2 acceptable options, let's look at the inference throughput. And it seems both of them perform pretty similarly, so that's good. But let's look at the fine-tuning throughputs. And we can see that the blue curve, FlexLLM, does almost like 4 times as well as the red curve. So if we want to maximize everything, we really should take the FlexLLM approach. Now, instead of the separate approach, we can just try to use different approaches for multiplexing. So FlexLLM is definitely not the only way to multiplex the 2 workloads on the same GPUs. So there's some approaches that are even simpler. For example, one approach is temporal sharing. So what we can do is simply alternate between inference and fine-tuning passes with different frequencies. So we should, if we want to meet the inference SLO, we should we should kind of like dilute the fine-tuning passes as much as we can, because otherwise those take much longer and will break the SLO. So we try different frequencies that try to optimize the throughput and while maintaining SLO. And you can also use a dynamic frequency. So the frequency of alternance can be determined based on the load. And then finally, you can also have spatial sharing. So you can simply divide the SMs from the GPUs for the 2 workloads and run everything in parallel independently. So once again, let's first take a look at the SLO attainment. So low arrival rate, everything looks good. High arrival rate, if you want to have at least 95% SLO, or even 90%, the only acceptable curves are the green, blue, and red curves. So FlexLLM, and then 2 temporal sharing approaches with different frequencies. And inference throughput, once again, just like in the previous plot, all these 3 curves do pretty much the same. So really, we need to look at the fine-tuning throughput to make a decision. So let's take a look. So the red curve is the lowest one. Green curve is in the middle. And FlexLLM, pretty much at all arrival rate, is higher than the other one. So once again, we demonstrate that FlexLLM is a preferred approach if you want to multiplex on the same node. And then finally, a case study. So okay, given that we're using FlexLLM, but we want to make sure that we can dynamically adapt to the bursts as they come in real time pretty quickly. So because otherwise we will break the SLOs when there's the change. So to check that, we ran a workload, a very bursty workload. So we can see here that the arrival switches from 0 requests per second to 4 requests per second on the left. That's the arrival rate plot. And on the right, we can see how FlexLLM does. And you can see that there's basically no delay. As soon as you have a burst in inference arrival, then we immediately dial back on the fine-tuning. In fact, the decision on whether to do some inference or fine-tuning work is done for each forward pass. So really, the only delay will be a few milliseconds that it takes to complete a forward pass. And crucially, FlexLLM can do it automatically. So there's no need for the user to intervene when the workload changes. So in conclusion, to summarize, FlexLLM is the first system that allows you to co-serve LLM inference and PFT fine-tuning on shared GPUs. And by co-serving, we mean that we can actually fuse the 2 workloads using the same backbone and the same kernels for the forward pass. And thanks to graph pruning and dependent parallelization, we're able to automatically parallelize the work in the optimal way and save up to 80% of memory, making it feasible, really, to run the 2 workloads jointly on the same GPUs. Incremental fine-tuning, so token-level fine-tuning and level layer fine-tuning, allow us to maintain strict inference SLOs and be extremely reactive. So as soon as a burst comes, we can immediately react. And finally, our end-to-end evaluations show that we have a fine-tuning improvement of up to 4.8x under heavy loads and up to 6.8 times under light loads. We evaluate on standard models of different sizes, and all our work is open source, so you can check out the project page or scan the QR code if you have more questions. Thank you very much, and happy to take any questions.